I want to talk about the energy in nuclear reactions. There are two categories. The energy in a nuclear reaction is separated into two different parts. So I told you that energy is the same thing as mass, even though in everyday situations the mass associated with energy is something we can ignore. In nuclear reactions we can't ignore it. We have to really take account of it, or else we won't be able to understand why things happen the way they do. So we can divide up the energy of a nuclear reaction into two different categories. The first one is called the rest energy. So let's take for example a proton, which I like to represent as red. Proton has a mass which is which is 1672.5 times 10 to the minus 30 kilograms. The neutron has a mass which is almost the same, 1674.8 times 10 to the minus 30 kilograms. Now in class the other day we did a calculation where we took this famous equation from Einstein, E equals mc squared, and we calculated the energy, which we were able to calculate the mass associated with different energies. This time we're going to use it the other way around. So I'm going to find out what energy this thing corresponds to, because I'm interested in how much energy is going to come out of a nuclear reaction. So if I take this mass here and I multiply it by c squared, remember c equals 3 times 10 to the 8 meters per second. C squared then must be 3 times 3 is 9. 10 to the 8 squared is 10 to the 16 meters squared per second squared. Okay, so I can multiply, so if I use this formula I can take this m, multiply it by c squared, 9 times 10 to the 16 meters squared per second squared, and the result I get will be, for the proton, 150.320 picojoules. Remember that 1 picojoule, pico is a word which means 10 to the minus 12. So 1 picojoule is 10 to the minus 12 joules. Okay, so that's 150 picojoules. Now, if I do the math here, if I multiply this also by c squared, turns out that the answer is 150.525 picojoules. So these are the energies which are stored, you could say, in the mass of a proton and a neutron. So the proton and the neutron in itself, because they have mass, they must have energy. In fact, you could say that anything with mass is made of energy in a sense. Almost, this is why at the beginning of the course I said the universe is made of energy. So actually everything with mass seems to have energy, and seems to have its mass because it has energy. It's a strange thing to think about, but that's the way it is. So this is the rest energy. So And we can calculate the rest energies of various other things. Electrons, neutrons, all these other particles have rest energy. Okay, so to find out the energy of a nucleus, first you calculate the rest energy. The second piece you need to use is the separation energy. Now, what is separation energy? Well, suppose I take a neutron and a proton. If I stick them together to form a nucleus, this nucleus I call 2-hydrogen. Sometimes it's called deuterium, and that was one of the nuclei that was on that worksheet in the lab the other day. In a nucleus like that, the proton and the neutron are stuck together. They're stuck together by something called the strong force. They have a kind of stickiness, and they don't want to be pulled apart. So in order to get them apart, if I was going to break them apart and to just have a free neutron and a free proton, which each have these energies, if I was going to get them apart, I'd have to add some more energy. So if I added energy, I could pull them apart, and then I would get a neutron and a proton separate. Now, I can calculate the rest energy of the neutron and the proton. I can find out what they are. But the funny thing is that if I had to add energy to the hydrogen 2 to get a free neutron and a free proton, that means that the hydrogen 2 must have less energy than the free neutron and the free proton. That's a little strange, isn't it? But it's true. The hydrogen 2 has less energy than the neutron and the proton. The difference in energy between the hydrogen 2 total energy and the total energy of the free neutron and free proton just floating along separately is called the separation energy. So the separation energy, which you will look up in the table, is negative, because free particles, free protons and neutrons, have more energy than nuclei where they're stuck together.